85, the remainder.
Sure. All right. So let's take a look at the remainder and factor theorems. Let me pull an example up to make it easy on us. All right, let's take a look at an example such as we have a function f of x equal to x to the 7th minus x to the 5th plus x to the 3rd minus x. And the question is x plus 1 a factor of this? Now, when do you know if something is a factor? If what? Okay, if you do long division and there's no remainder, or synthetic because we're dividing by a factor that's only a binomial here, and the binomial has a linear coefficient or unity coefficient. As long as there's a 1 here in the front, you could use synthetic. I would definitely use synthetic. I would not use long in this. This would be messy as anything for long. So let's draw a quick synthetic table. On the outside, what should I put, Mike?
1.
Careful.
On the outside? Oh,
Yeah.
sorry, negative
Negative
1.
1.
Yeah.
And then on the inside, go ahead, start along the top, I guess.
1. Isn't next 0? And then another 0.
No, you got negative 5th there.
Oh, right, sorry, 1. The negative 1.
Good.
And then a 0. And then negative, positive 1, sorry. And then 0.
And then?
Negative 1.
And then?
Uh,
Wait, yeah, there's no constant, right? This is really annoying. See what they're doing here? 1, 0, 1, 0. It's just going to be a messy multiplication. Remember, at the end here, there's really a plus 0, isn't there? Whatever the constant is always goes at the end. There's no constant here, so don't forget about it. So to figure out if this is a factor or not, we simply plug in the opposite of that number. This is like, remember, x minus c. If you want to know if x minus c is a factor, plug in c in the table. So if we want to know if x plus 1 is a factor, plug in negative 1 in the synthetic table. I'm using synthetic substitution, obviously. So this is using our factor theorem. All right, so let's take a look here. We bring down the 1. Negative 1 times 1 is negative 1. Negative 1 and 0 is negative 1. This is just a lot of room for error. Do you see this right now? What's about to happen? It's going to go back and forth with 1 and negative 1 and signs changing here. So we're going to get a positive 1 plus a negative 1 gets you back to 0. This is going to be 0, and 0 keeps you at 0. 0 and 1 makes it 1. Negative 1 and 0 is negative 1. Positive 1 and negative 1 is 0. 0 and 0 is 0. So the remainder is 0, therefore it is a factor. Okay, it is a factor. Now, the remainder theorem is simply the idea that when you divide when you have a polynomial and you divide it by another polynomial, the remainder is like that additional piece on the side of it. And we proved that. If you look back in your notes, you can see that. And what it's really saying is your dividend equals your quotient times the divisor plus the remainder. But all this is saying really is when you do long division here, so you divide some function g of x into some function f of x, and the result is r of x plus some remainder r. Literally take these and think about it. What you're doing here is you're saying, in this case, you have this f of x divided by g of x, and your result is this mixed number here. Okay, and it's an expression, that's what we're going to see here. We didn't really, directly talk about the remainder theorem in this sense, but the idea that you want to know in this lesson is that the remainder is really the y value. When we talked about graphing, that's where we applied it. The remainder is really the y value when you plug it in synthetic substitution. So that example we did a moment ago, when we looked at that, if you ever plug into a table, say you plug a 2 into some table, and let's say the numbers are just a bunch of random numbers, I don't care what they are. You get all these numbers as an answer, it starts at a 4, and then the last number is 3. This is not now, again, this is not a root of the function at this point because you didn't get a 0 here. But it does still have significance. It tells you that when you plug 2 into the function, the y value is 3 that comes out of it. Okay, this is what we really honed in on when we talked about this. We mainly looked at that and then the factor theorem for it. But, obviously the factor theorem comes from the remainder theorem. When the remainder is 0, it is a factor. So that missing remainder is telling you it's a factor there. What else? What else? Upper bound and lower bound? Sure. So let's take a function and let's say f of x is equal to x to the 5th minus 2x to the 4th plus 3x to the 3rd minus 2x squared plus x minus 5. In a problem like this, we can look at differential signs that tell us the amount of possible real, positive, or negative roots, and then we could also look at upper and lower bounds when we plug into a table. So, Zavini, you want to specifically look at upper and lower bounds? Is that your question? Okay. So we start with our table. We have 1, negative 2, 3, negative 2, 1, negative 5. Now, the upper and lower bound, the idea of these boundless theorems, don't apply until you pick a number to try. So usually you start this kind of a problem by making a list of possible rational roots by looking at p's over q's. So just looking real quick, I can see that p values are possible of 5, right? Negative 5, 1, and negative 1. And q is only 1 or negative 1. So the possible values to plug in right now should be 5, 1, negative 5, or negative 1. So pick one of those. Charles? 1. I agree. I'd always start with a 1. 1 is easier to work with. So we have 1 times 1 is 1. 1 plus negative 2 is going to give us negative 1. We're going to get a negative 1 here, plus 3 is going to give us a 2. We're going to get a 2 here, plus negative 2 is going to give us a 0. 0 plus 1 is going to give us 1. And 1 plus negative 5 is negative 4. Now, if you had plugged in a positive number and got all the same sign, it means it is an upper bound. You plug in a positive number and all signs are the same, it is an upper bound. Only when you plug in a negative number do you test for a lower bound. So let's look at the next example, because they're not all the same sign clearly. A lower bound, we have to look for alternating signs. Let's try 5. Let's keep it positive. 5 times 1 is 5, and negative 2 is going to give us 3. It's going to give us 15, and 3 is 18. 5 times 18 is going to give us what? 90? 90 minus 2. What's going to happen as I keep going? The numbers are going to keep getting bigger. Am I going to keep adding these numbers? No, but I'm going to recognize that they're all going to be what? They're all going to be positive. I don't really care what they are. I know they're going to be positive. It's got to be. You're taking 5, multiplying by a positive number, and then adding this minuscule value up here, whatever these are. They have no significance. So this is an upper bound. Okay? So what this tells us is that there are no roots above 5. There are no roots above 5. So we still have to try negative 1, obviously. Let's go ahead and try negative 1. Let's see if that's a rational root. Bring down the 1. We get negative 1. Negative 1 or negative 2 is negative 3. That'll be positive 3, and 3 is 6. That'll be negative 6, and negative 2 is negative 8. This is going to be positive 8, and 1 is 9. This is going to be negative 9, and negative 5 is negative 14. So what's the deal here? This is a Lower bound. How do you know that, Luca? Alternating signs. So that means that the possible rational roots, or the possible roots of this function, actually, possible roots not necessarily rational at all, because we've tried the rational roots. Why would we not even try -5? Because this is a lower bound. You can't go below a lower bound. That's what a lower bound is. So it's got to be between -1 and 5. We've tried all the possible rational roots between -1 and 5. So the roots must be I thought I heard the word. I heard you all say it.
I said in between negative.
Yeah, but I said we tried all the rational roots between -1 and 5. So they're either irrational or the roots are what? What's the other option? Imaginary. Yeah, imaginary. Okay, now what's the degree of this equation? So what's the possible combinations? Let's go through them. You should know this. What are the possible combinations of roots that you could have? You could have 2. Okay, 2. Now, remember that imaginary always come in pairs. Irrational could come in odd numbers. They don't always have to. When we solve, because no, and I think when I was teaching you guys quadratics, I think I said they always come in pairs. With the quadratic formula, they do, obviously. When you solve a quadratic and get irrational roots, they're going to come in pairs, right? With the quadratic formula. But you could have an odd number of irrational roots, but you have to have an even number of imaginary roots, okay? So let me, maybe I made a mistake when I said it. So you could have 2 imaginary roots, right? And then 3 irrational. That's one option. We know that there's going to be no rational roots. What else? Kelly?
4 imaginary and 1 irrational.
Okay. And last but not least?
All irrational.
All irrational. Okay? Those are our possibilities. Simply because of the fact that it's x to the 5th. We know there's no irrational. The imaginary has to come as either 2, 4, can't come as 6 because there's only 5 total, so you stop there. And then we have to know that these have to sum up to 5 always. Okay? All right. What else? Another section. These are good questions. These are not easy questions either.
Could we go on with the discriminant?
Discriminant, sure. So let's look. We looked at the discriminant several ways. So let's first of all quickly state what it is. And then let's look at maybe 1 or 2 examples that we can see how they would be applied. So what is the discriminant first? What is it?
B squared minus 4ac.
Good. So let's take a look at how it's applied. Okay? If the discriminant is positive, and we recall, when the discriminant is positive, what we're really looking at is what's underneath a radical. Remember this. If there's a positive under a radical, the roots have got to be real. What else? It could be irrational or rational. Let's talk about that. When is it irrational? If the discriminant is not a perfect square. If you have a number under here, let's say b squared minus 4ac equals a number like 17. If that happens, then you take the square root of 17 in the formula, which makes it irrational for sure. So when are these roots going to be rational? When it is a perfect square. Okay, and again, by the way, we're assuming that a, b, and c are integers. If, for example, if b had been like the square root of 2, imagine the coefficient was root 2, it wouldn't be rational then, because you'd have a root 2 out here. Imagine if b were root 2x, you know what I mean, in the quadratic. So considering that all a, b, and c are integer values, by the way. Or rational values, I should say. So for example, a number like 16. What else? If they're irrational, what do you know? If they're irrational, what do we call them? What's the term? It's a word for the roots that are irrational roots. What is it? Binomial conjugates. Okay, binomial conjugates. Binomial meaning 2 terms. Conjugates meaning 1 is plus, 1 is minus. That comes from here, plus or minus. They're also distinct, meaning different. In both cases, they're distinct. They're just different roots. When the discriminant is 0 at the bottom down here, this entire thing drops off. Imagine taking this whole thing right here and making a 0 out of it. Well, that means you reduce to negative b plus or minus 0 over 2a. So it's just negative b over 2a. Plus or minus 0 has no effect on a problem. So you end up getting one repeated root. One real repeated root. And when I say one, obviously, you'd have two roots, but it's just a repeated root. You could say it's a root with multiplicity of 2. It's another way of saying it. Okay? And last but not least, negative. That's the answer automatically. If it's negative, you have what kind of roots? Imaginary. What do we call them? Complex conjugates. Good, Josh. Now, with that said, I could give you any quadratic and say describe the roots as fully as possible using the discriminant. And you would literally do this. You would determine the discriminant and you would make this exact statement, or this exact statement, or this whichever exact statement. Does that make sense? When you hear describe the roots as fully as possible, you're literally writing what we wrote in those boxes based on what you get for a discriminant. That was one option for these problems. The second option, or the second thing to recognize, was graphically. If the discriminant is positive, you have something like this. 2 real distinct roots. So you have 2 x-intercepts. That's when the discriminant is positive. When the discriminant is 0, you have a tangent point somewhere. It might open down, it might open up, I don't know. I'm going to say they're all opening up for now, but you have a point of tangency right there. And the point of tangency is that one repeated root. It occurs twice at that location. So this graph is never below the x-axis, or maybe it's never above. But whenever you have a real repeated root, you have to have a point of tangency there. So this is when the discriminant is 0. And last but not least, when the discriminant is negative, you have no roots. Sorry, no, I should say real roots. So no roots appearing on the graph, or no x-intercepts on the graph. Now, there was one other thing we did. Let's say I give you the following. Bless you. Was that a sneeze or a cough? Let's say and let's call it f of x, not 0, sorry. Let's say we have the function there, f of x equals 2x squared plus 5x minus 2k. And the question says to you, determine the value of k, or values of k, with a parenthesis on the s, that cause this function to have one real repeated x-intercept. The graph of this function has only one x-intercept, determine the value of k. So look at over here. When does it have one x-intercept? When the discriminant is 0. So what are you going to do about it? What do you got?
We just plug in for x, right?
Not for x, no. Remember, when the discriminant is 0, right, is when we have one x-intercept. So if the question says, find the value of k so that there's only one x-intercept on this graph, you have to set the discriminant equal to 0. Because they're told that the discriminant equals 0 when there's one x-intercept. So take a look at the discriminant. B squared minus 4 times A times C, and that's got to equal 0 for one x-intercept. And then solve for k. This is an easy one, right? This is the easier version. K is an integer, or a single value. Move the negative 25 over, divide by 16, so you get negative 25 over 16. That's the value that k has to be for this discriminant to equal 0, or for there to be one x-intercept. It doesn't have to be an integer value, it's just a value. What if it had not said one x-intercept? What if I said for it to have no x-intercepts? Determine the values of k, or the solution set, give you a hint there. Determine the solution set for k so that this graph has no x-intercepts. Which of these three options has no x-intercepts? When the discriminant is negative, which is less than 0. So take the same discriminant we just had and set it less than 0. So we have 25 plus 16k less than 0 now. Well, take a look. What's going to happen here? We're going to still get, in this case, k is, let's see, we're going to subtract the negative over. It's not going to switch the sign. It's going to be less than negative 25 over 16. So there's many values that you can plug in for k. And go ahead and do me a favor and grab your calculator and take a look at this. Go to line 1. Type in the function up there, but where you see a k, leave it blank for a moment. And we'll pick a value together and choose.
Wait, we're plugging the top.
So plug in the original function at the top, but just plug in the negative 2 at the end. Don't type in what k is going to be at. Put negative 2 and then just put like a times symbol. Or put a parentheses after the negative 2. Because you're going to have to multiply it by a fractional value to check this one, right? So in your y1, you should have 2x squared plus 5x minus 2 open parentheses. That's what this should be there right now. So for the first function, let's try the negative 25/16 exactly. So in the parentheses next to the negative 2, type in negative 25/16. We're just going to vary that value, so leave it for now. We're putting a placeholder in. Okay, so put a value for pain. Why do you confuse them? What's that? So literally type the equation in the way you see it, but where you see a k, put a parentheses, and inside the parentheses, put this value. We're going to put a placeholder in y1, so we can keep varying that placeholder. So put a parentheses after the negative 2, and then put a negative 25/16 in that parentheses. So that it multiplies the negative 2 by the negative 25/16. In Zoom 6 or graph or whatever. Take a look at Ben's. Yours should look something like this, but what do you notice? There's only one x-intercept, and that's what we did in the first case. We set the discriminant equals 0, so there should have been a point of tangency on the curve. Okay, so that's what it looks like when we plug in negative 25/16. What is negative 25/16 approximately as a number? It's between what integers? Negative 1 and negative 2. Very good. So if we want something less than this, pick a number that's far less than it to see the next thing, right? Let's pick negative 3. So in that parentheses now, instead of putting this in y1, you could put just positive 6 at the end, or negative 2 times negative 3. But change the parentheses from negative 25/16 to a number much less than it. Okay, so pick negative 3 just for the sake of it.
Wait, so just keep everything the same?
Keep everything the same, except what was in that parentheses at the end, make it a negative 3. That's why I had to put the parentheses there, so you can sit here and just tweak that number. Yeah, you should get no roots now. You should have no x-intercepts. It should be floating above the axis. It should be floating above the axis. It might not even be showing up in your graph. It's possible. Is it showing up now? You gotta put a negative sign in the minus sign. Yeah, perfect. So what you're doing, right? Think about what you're doing, guys. It should be floating above the sun. Think about what you're doing here, right? Look at the C value. Let's pause and step back, because this is a really good lesson, actually, because now we're learning about y-intercepts too. The C value is your y-intercept of a quadratic. So in this case, you plugged in negative 2 times negative 3, which is what? What's the C value in this last one you just plugged in? 6. Again, negative 2, and you chose negative 3 for k, so C is really 6. Look at your graph. Where's the y-intercept? It should go through 6. So what you've done here is this. Think about it. Ready? You've taken the same graph, and by changing the C value, you are doing a vertical shift on it. You're going to learn a lot more about this in pre-calc. You're going to study about functions and shifting a lot more. Okay? And you're doing a vertical shift, really. We talked about this as being a y-intercept. If you keep adding that value, you're talking about shifting it vertically. It's like looking at a quadratic in vertex form. a times the quantity x minus h squared plus k. If you keep raising k up, you keep changing the vertex, you keep moving it up. So if you pick a number now, in this case, if we want to figure out the other way, where there's two x-intercepts, we need the graph to not shift up, but shift down. So if this is the x-axis, here it was when it was tangent, we just shifted it up, now we need to shift it down. But we recognize that to shift it down, we want to make that number more negative. So this number should be probably positive or something, so that number ends up being negative. Well, let's go ahead and solve for that case. That's the third case now. So the third case is if we want two x-intercepts, we need to have the discriminant greater than 0. So this value just changes to greater than. Think about it. Everything's the same. This equation is the same here, except this is a greater than now. So you could write it out again if you want. B squared minus 4ac is greater than 0, and you'll get k should be greater than negative 25/16. Well, again, negative 25/16 is between negative 1 and negative 2. So a number bigger than negative 1, you can make it 0 if you want. Go ahead and make k 0, or make it 1, or 2, or 3. But now make k a positive number, or 0, or a positive number. Something bigger than negative 25/16. It doesn't matter what it is.
Do you need to know the h of the h minus k for the final exam, or will you have it on the test? Really? How do you say it? Like, the k forms it around the equation?
Should you know the vertex form of quadratic?
It's like, yeah.
You should. You should absolutely know. So like, the vertex form is f of x equals a, parentheses, x minus h squared plus k. You should know that h and k are the vertices. A dictates the concavity, the width.
But do we need to know the actual formula?
Like,
His
should you know
his
this?
doctrine should be like
Should you know vertex form?
Yeah.
Should you know standard form? Yeah, you should.
Yeah.
I'm trying to think if I think that at some point in the test you're going to probably be given a problem that's in vertex form. You'll be able to recognize it, but you should know that it's x minus h and a plus k and know what to do with those values. Okay, so you try a number, you see that there's two x-intercepts now, yes? Check. Okay. All right. Enough time for another one. What else you want to do? We covered. Okay. What else? What else?
Were you over the thing? I forget what it's called, but the one with the critical points and stuff and the number line?
Critical points on a number line, so quadratic inequalities.
Yeah.
Now, it's funny that you asked that because quadratic inequalities can come up with that last topic also. If k, remember the last example we just did? K was over by c. If k was by b, you would have k squared. So you'd have to use a quadratic inequality for that one. That's a little complex. I don't think I have that on the final. I could look to see, but that's something that we definitely covered. But that'll apply to this. So let's take a look. So let's say we have x squared plus 5x minus 14 less than or equal to 0. Let's make it tougher. Let's make it x cubed. Raise everything by a degree. Make this x cubed. Make this x squared, and make that a negative 14x instead. When you see me do that, obviously you know what I'm going to ask you to do first. What should we do first? Yeah, start by factoring out that x I kind of just added in there. And I'm doing that on purpose, so it just makes it a little bit tougher. So you can see 3 sections on a number line instead of just 2. Okay, next. Yeah, what do you got?
X plus 7 and X minus 2.
Okay. What are my roots or my critical points in this case now? They're not really roots now, Kel?
2 negative 7.
It's what?
2 negative 7 and 0.
Yeah, and 0, don't forget, good. 2, negative 7, and 0. Now, I'm putting equal signs, but on the side I'm going to write CP so I remind myself that they're not really equal. Now, when it's an equation, you get 3 answers. When it's an equality, you get a set of answers. So to find that set of answers, we go ahead and graph a number line, and we use our boundaries we use our critical points as our boundaries. So 0 is there in the middle, 2 is over here, and honestly, it does not have to be drawn to scale, so don't worry about that. Okay? What do we do next? What do we do next?
Test points.
Test points. Now, where should you probably test points to make it easier on yourself? This is one of the times you're not going to go back to the original. This is assuming you factored correctly, though. That's the thing. If you factored incorrectly, you might test these points in the incorrect factors. Luca?
You test the points in the factor.
The factored equation, the factored form, because it makes it easy to look at positives or negatives, and that's all we care about. So pick a number bigger than 2. 3. Don't go any further, please. Plug in 3 right here. That's positive. Plug in 3 right here. That's positive. Plug in 3 right here. That's positive. Positive, positive, positive is clearly positive. Next region. Remember, it doesn't matter what the number is. It's whether it's positive or negative. Test a 1 next in here. Positive, positive, negative. And what's going to happen next, probably? Yeah, it's going to alternate, as we've seen. Take a negative 1. We get negative, positive, negative. A negative, positive, negative is back to positive. It's a double negative there. And then testing negative 8 over here. This is a negative. This is a negative. This is a negative. A triple negative is still negative. This original question asked us, when is x less than 0, right? When is the whole quadratic, or what value should x be, so that this whole quadratic here, or trinomial I should really say, is less than 0? So when is it less than 0? In what regions? In what regions is it less than 0, Ben? In what regions on the number line?
0 to 2 and below negative 7.
0 to 2 and below negative 7. Should I do anything specific beyond that? I need to do one more thing.
You need to like write it out. I usually set.
I can write it out, but you're missing one thing. Come on, real quick. Besides that, on the graph, I should do what to those circles?
Oh, you should color them.
Color them in.
Yes, that are-
They're included in the solution set. Now, had the equation had said greater than or equal to, I would have shaded the other regions. So from negative infinity to negative 7, I would write it like this. I would use interval notation here, just because it's easier. Remember, the bracket means inclusive. So if it's a closed circle, you use a bracket. Remember that infinity can never be reached, so we put a parenthesis showing that it's not included in the solution. Another way of writing this could be, did I do y or x? I did x. I don't know why I'm writing y. Another way to do this, x less than or equal to negative 7, or 0 less than or equal to x less than or equal to 2. So you have interval notation and set notation. Okay? Those would be your two solutions for this problem. Good question. One that's definitely worthwhile looking at. A problem like this is very much like the problem you can see on a final because it includes factoring, it includes the idea of roots, it includes the idea of number lines, testing points. So you could definitely expect something of this difficulty level where you can combine a few different topics. All right, let's stop there.